Cool. Now let me share my screen. Okay, so everyone should be able to see the worksheet on my screen. And let me make sure I have chat visible. Okay, cool. All right. So yeah, let's get started with it. My plan was actually for the moment to skip problem one, because as far as I can tell, there isn't anything specific to the most recent lectures we've been doing in the solution of problem one. I think you can solve this one with just the knowledge of equivalences that we got from Ulrich a handful of lectures ago. At least that's what I see. So that might be a good exercise to check your knowledge from that stuff. But I think I'll skip it for now and go right to problem two here. All right. So problem two is asking us to consider a family of types over A. Oh, sorry, still got the highlighter. So yeah, we have this type family, and the assumption is that each of the BX's is a proposition or contractible. We'll consider both cases in this problem. So in each of those cases, we want to show that it's also the case that this pi type for all x in A, BX is a proposition, or in the case of contractible, it's contractible. All right, cool. So yeah, let's start on this page. So problem two. So we'll do the proposition case. Suppose that each of these types is a prop. And we want to show that this pi type is a prop as well. All right. So let's recall that to show that a type is a prop, we can do it in a few different equivalent ways. Often the most convenient way is to consider two arbitrary elements of the type in question. So in this case, we have two dependent functions in this pi type. So once we have that, we want to show that these two arbitrary elements are actually equal. So we want to show that we have a proof that this identity type is inhabited. All right. So we have these two dependent functions. We want to show that they're equal to each other. So this is an instance where we'll use a very, very convenient fact in our type theory that we just introduced yesterday in lecture, and something that I'm sure a lot of you have wanted to use in the past, which is function extensionality. So, so use function extensionality. Then, in this case, we just need to show that f of x equals g of x for all x in A. Okay, so so for each point in the domain, we need to exhibit a term of this identity type. And this, just to be clear, this lives in B of x. And all right, so let's okay. So let's think, can we construct a term of this type here, this identity type? Well, let's think. I mean, how would we proceed? There's nothing, this B of x is kind of an arbitrary type at the moment. These terms are just kind of arbitrary terms of B of x, you know, f of x and g of x. So we probably need some data that we've assumed to go forward. The only assumption that we have at our disposal is the assumption that each B of x is a prop. If we have that each B of x is a prop, can we find a way to construct a term of this identity type, f of x equals g of x? Any thoughts? So I'm asking, if b of x is a prop, which we know by assumption, does it follow that f of x equals g of x? Which is exactly what we need to show here. So, oh yeah, okay, so we have a comment in chat. Yes, yeah, so, yeah, okay, so we have two comments. Yes, the fact that it's a prop implies that, I think what you're saying, Christian, is that the fact that b of x is a prop implies that this identity type is contractible. And then Antonio says that, yes, this is inhabited. So yeah, so both of those things are true. In particular, we just want to know that this identity type is inhabited. In fact, it's contractible, as Christian says. So yes, so great. So since b of x is a prop, the identity type is inhabited. And in fact, it's contractible. This is a parenthetical note here. Cool. And yeah, and just to be clear, the fact that b of x is a prop means that for any two endpoints, you know, where f of x and g of x are placed, we would have that the identity type between them is inhabited. Okay, so yes, it holds. All right, so that was the proposition case. For practice, let's also consider the other case. So now let's instead assume each b of x is contractible. It's a little messy. Is contractible. Okay, so now so now we want to show that the pi type here is also contractible. All right. So now instead of assuming it's a proposition, we can now do a little bit more because B of X is contractible. So since we have a term, let's call it little c of x, such that for all, let me use a different variable name here. For all z in B of x, we have a path from C of x to z. That's really messy. All right. So that's what we get from the contractibility assumption. When B of x was just a proposition, we didn't know that we actually had an element of B of x for which every other element was identical to it. We just knew that any two terms of B of x were equal. So now that we have this C of x, which from the lecture and book we call, for terminology, we call this the center of contraction of B of x. We also want to, we want to find now a center of contraction for the pi type. All right. Well, so in particular, what that means, if we want a center of contraction for this type, we need an element to start with of this type. So let's just think at the moment of what we can pick as an element of this pi type. So let's just, without even worrying at the moment of if that element will be a center of contraction, let's just think of what options do we have to construct a term of this dependent function type. Given that we have a center, the C of x for each B of x, what can I choose for a function in this type? So I'm looking for each x in A, I'm looking to output an element of B of x. So what can I choose for this spot? Yeah, so in the comment we have an answer that we can put. Yeah, exactly. So so in the comments, I'm seeing that we can choose for this dependent function lambda x and then output C of x. All right. Now, so now, okay, so we have this inhabitant of this pi type. We want it also to be a center of contraction, meaning that every other element of this pi type is equal to this. Now, we could perhaps do this explicitly, find a proof that for every dependent function here, we have that G equals this function here that we constructed. We can kind of use a stronger thing right away and be done. And this is often convenient and useful, so I want to do it here. So to recap, we have a element of this pi type with this function, so it's inhabited. Recall that to show that a type is contractible, it's enough to show that the type is inhabited and that any two elements of that type are equal. So in other words, it's enough to show that the type is a proposition and it's inhabited. So we have the inhabited part. So it remains to show that the pi type is a prop. And this is where I want to use sort of a shortcut that we know to conclude this. So what can we do to conclude that this is a prop? Any ideas for, so right now the thing I'm asking about is how do we know that this pi type is a proposition? Any ideas on how we can argue for this? Yeah, so in the comment, we're like, there's a comment, haven't we showed that this is a prop? And I think you're referring to the previous thing where, so in the previous part of the problem, we showed that if each of the b of x here is a prop, then this entire pi type is a prop. So yes, so to answer your question, yes, if we can say that each b of x here is a proposition, then we're done by the previous part because we showed that the pi type is would be a proposition. Now, technically, we've in this part of the problem, we've instead assumed that each b of x is contractible. So b of x is contractible. So technically, that's not the exact same thing as assuming it's a proposition. But now I want to, so this is kind of where I'm asking us to just use a shortcut from something we've already proven in the past. So I'm asking is this enough? If we know that b of x is contractible, do we know that it's a proposition? Have we seen such a fact? Well, okay, I guess it's a little, I guess at this point, I'll just remind you that in lecture, we've seen that any contractible type is also a proposition. Okay. So in particular, remember that if a type is k truncated for a truncation level k, then it's also k plus 1 truncated. Okay, so if you prove that a type is truncated at some level, then it's also truncated at all the levels above it. But here we just needed a very low level, which is that contractible types are also propositions. All right, great. And also I do want to, that was kind of that is a fact that we've seen, I wanted to remind you of, but also it's also pretty easy to see directly that contractible types are propositions, right? I mean, you always, if it's contractible, any two terms in that type have a path to the center of contraction. So you can just, so so if I have the center of contraction and I have these two terms, then we can have paths to the from each term to the center of contraction. And then to show that those two terms are equal, I can just go down here and then concatenate with the inverse to get a path from Z1 to Z2. Okay, so you can see it directly, but I kind of just wanted to use this moment to remind you of the fact that we have this hierarchy of truncation levels where if it's a K truncated type, it's also K plus 1 truncated. All right, cool. Any questions on this this problem here? Problem 2. Okay, so we have a comment. The proof that they are propositions in the sense, so the proof that, okay, I think the comment is that if you try to prove that a contractible type is also a proposition by showing that for any two terms in this contractible type, its identity type is also contractible, is harder. Yeah. So yeah. So yes. The proof that any identity type is a contractible type is also contractible is yeah, it is a bit harder to do. Now I don't quite remember. Was this an exercise on maybe worksheet 6, the fact that the identity types of contractible types are also contractible? Oh, okay, it's in lecture. Yes. Yeah, that's a good point. It's a good point that is more difficult to show. Yeah, it is interesting that yeah, it is interesting that when you pass to the equivalent definition, okay. Yeah, it is interesting that when you pass to the equivalent definition of propositions where any two elements of the type are equal, it becomes pretty easy to show that contractible types are propositions. But when you use sort of the original definition of proposition, where the identity types are contractible, then it is more difficult. Yeah, I guess it was in lecture. I thought it was also somewhere on a worksheet of worksheet 6 or something like that. But yeah, it's a good point that it does become more difficult. Anyway, okay, yeah, in the interest of time, I want to get to problems 3 and 4, so I better start. Cool. So yeah, so let's look at problem 3 here. So part A, so secretly, we're not secretly, but in the background, we're letting A be an arbitrary type here. And for part A, we want to show that the type is contractible. The type A is contractible is a proposition. And let's see, I think in the footnotes, I thought that there was a footnotes telling us what this stands for. But anyway, let me just let me remind us that this was well, this is the same as saying that there's an element of A such that for all other elements of A, we have a path from X to Y. Okay, so we want to show that this type right here, this sigma type with a pi type nested inside of it, is a proposition. Okay, so this holds for any type A. Okay, cool. Yeah, let's start with so this is problem 3, part A. So if we want to show that that is contractible A is a prop, let's use this convenient definition we've been using of proposition, where we let, so we're gonna take two arbitrary elements of this this pi type here, and we want to show that they're equal. Now, we can now use sigma induction to take our two arbitrary elements of the type is contractible A to be pairs. Okay, so really what we're doing here is we're going to take two pairs, A1, P1, A2, P2. So we're going to let these be elements of is contractible A, which again is this sigma type. How did I write it up here? X equals Y, sure. So, okay. So we have these two pairs, and we want to show that we have an identity between them. Now, recall that to prove that we have an identity between two terms in a sigma type, we want to show that this is exactly the same as showing that we have, this is not readable. So yeah, let me be clear. We want to show we have an identity, and let me call this Q. So we want to show that we have a path Q between A1 and A2, and we want to end a path where we transport over Q so the transport over Q applied to P1 is equal to P2. And yes, and so this transport takes, the type family of this transport is it takes an element of X in A, big A, and it outputs a pi type, saying that every element of A is equal to X. So this is what the transport is over, taken over. We want to show that we have a term Q and a path of this type here. All right. So let's start with finding a path little q between A1 and A2. All right. So let me ask you guys, what's a candidate for a path between A1 and A2 here, given the data that we have? So it might help to remember what types these terms in the pairs have. So P1 has the type, let me write it up here. So P1 is a dependent function that takes an element of big A and says that that element little y is equal to A1 here. So okay, so remember, so P1 is a function. It takes an element of big A and it says that that element, that there's an identity from A1 to that element, little y. So if I want a path from A1, so we could kind of take, so yes, we kind of take a project. Yeah. So good. So let me address a couple comments from the chat. So taking the projection, yes, I am sort of doing that here. I'm looking at the second projection of this pair, but because since I've already written this term as a pair, I already have a name for the second component. So I don't even really need to apply the projection to the pair here because I already have the name for the second component. I can just use it directly. And yes, and then the second comment, which gives a option for a path between A1 and A2, is so yes. So for Q here, take this term, this function P1, and apply it to A2, which exactly gives us a path from A1 to A2, which is exactly what we want here. Okay, great. So now it remains to show that, we have a path of this transport over P1 applied to A2. So we want to show a path of transport applied to P1, A2, applied to P1 to the second components here, P2. Okay. Now, so let's first think of where does this identity type live? So it's easiest, I think, to look at this endpoint here, P2, and notice again that this is a pi type that takes, let me, it's getting a little messy here, so let me get a new page. So, oops. So let me write this identity type lives in the pi type that takes an element little y of A and gives us a path from A2 to that element. All right, so really this transport here is so really this identity type between the transport and P2 is an identity type between functions, dependent functions of this type here. So now, in order to prove that we have an identity between functions here, what can we use? I mean, really the only tractable way to go about this is to use, again, functional extensionality. And now we want to show that, let me, for convenience, sorry, let me write. for convenience, let me call this term here K. Why not? So let's call that K. We want to show that K of X equals, well, you know, sorry to keep doing this. I want to be suggestive with my notation. And let me just use Y because that might make it a little nicer. We want to show K of Y equals P2 of Y for all Y in A. So this now lives, this identity type is an identity between paths from A2 to Y. Okay, so this is now what we need to show for each Y. We need to find a path of this type. Now, so is there a path between these? Is there a path between K of Y and P2 of Y? What do we think? I mean, we've done a lot of work at this point, so it might be hard to remember everything we have here. I'm not saying there's an immediately obvious proof that this identity type is inhabited, but do we have any ideas on what we could use? And again, I always want to remind you of what assumptions we have in the background, because those are often useful. And if we go way back, okay, this part isn't an assumption. We want this is what we wanted to show, but along the way to prove this, we have assumed two terms of the type is contractible A. So we have data in the background here that witness that A is contractible. Okay, so that's my hint. We have data, we have witnesses that A is contractible. So can we use that data to now prove that this term is inhabited, this identity? Sorry, to prove that this identity type has a term in it. So let me write it out. Sure. So yeah, no. So let me, so this is a little tricky. So let me, so we know, so we have, so we got a comment that if a type is contractible, then it means that that type is a set. That's true, although I'm not sure that is exactly what we want to use. So we know that A is contractible. We actually I don't think we need to use problem 2 directly either. So instead, let's just look at the fact that we know that A is contractible by either of the two witnesses that we've assumed of A is contractible? A1P1 or A2P2? By right? So we've you know, in order to assume that, in order to prove that A is contractible, A is a proposition, we've assumed, we've you know, we postulated two arbitrary terms of that type. So we have that at our disposal. We have a witness that A is contractible. So since we have a witness that A is contractible through, say, A1P1, what can we use? I mean, sorry, what can we derive from a proof that A is contractible? So using that A is contractible, I want to know if we can derive a term of K of Y equals P2 of Y. So there's a comment, we can connect the two terms. Yes, so you are right that I think you're saying that we can find a path between the two terms. Yeah. Now, I do want to, I want to, so you're saying we can connect the two terms to the center. I want to be a bit careful here because K of Y and P2 of Y are not terms of A, actually. They're terms of A2 equals Y. So in order to connect K of Y and P2 of Y through a center, we need to know that there's a center of contraction of A2 equals Y, the identity type A2 equals Y. So this is a good comment. So it suffices now to show that A2 equals Y is contractible. So that's where we've reduced it to that question. Can we conclude that A2 equals Y is contractible from any data that we have? So we have going back to what we had before, we have a witness, we have data at our disposal that from A1P1 that A is contractible. Can we conclude from that A2 equals Y is contractible and therefore conclude the identity type we want? So remember, A2 and Y live in big A, the type big A here. Sorry for the messy writing. Let me make that clearer. So any ideas? We have that A is contractible. Does that let us conclude that A2 equals Y? Okay, all right. So there's a comment, doesn't is set solve this? So I think what you're saying is, let me go back. So if A is a set, that means that if A is a set, then A2 equals Y is a proposition. So so do we yeah, 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 yeah. So, yeah, that's, I mean, yeah, that's a good point. Um, so we know, okay, so, yeah, I think I see what you're saying in the comments. Instead, why didn't we just, so instead, why don't we just use that, since we know, since A is contractible, we know that it's a set, and therefore, uh, this identity type is a proposition. Um, and therefore, any two elements of this identity type, like K of Y and P2 of Y, are equal. Correct? I mean, that should summarize, I think, what you were saying. Um, and yeah, yeah, great. So I had it. So that's the argument in the chat. And yeah, yeah, you're right. I should have. Yeah, that's, you're right. That would work too. And as long as you, yeah, using the implication that a contractible type is also a set, then you will, yeah, you will get a term of K of Y equals P2 of Y. Yeah, right, right. Yeah, that's, yeah, no, that's fine. Yeah, that's what I'm thinking. So I'm thinking about if the solution I'm getting at here is any nicer than using the implication that a contractible type is a set. I think it actually is a little nicer, because if we're using the definition of truncated types as a K truncated as a K plus one truncated type, let me think. You know what? You know, I don't think. Yeah, you know what? In this particular case, I don't think it's any nicer because what I'm using here is that. So okay, let me finish. So yeah, let me just quickly finish what I was saying here, and then that'll go right to this question from the chat. So so going back here, I was saying that it suffices to show that A2 equals Y is contractible, um, and uh, and and that's, and this yes, I now see that this is the case, because we've shown that any contractible type has contractible identity types. So since A is contractible, we also know that any identity type, and in particular A2 equals Y, is contractible. But that proof is a bit difficult, as we've been saying. So that that isn't so nice, I guess, because you need to prove that. You know, um, uh, yeah. Okay. Yeah. So anyway, yeah, yeah. No, I just was thinking. Yeah. But yeah. Anyway, the other solution where instead we have to prove that any contractible type is a set. Uh, that might be, yeah. That might be a bit easier. I'm not sure, but I'm not. I guess it's a matter of taste a bit. But anyway. Um, okay. So yeah. But this. So seeing the proof without using that. A contractible type is a set is just what I've been saying here, which is that since A is contractible, we know that A2 equals Y is contractible too, because we've shown in the past that a contractible type has contractible identity types. But as in the chat, it's mentioned that that proof is not so easy. So we are using a non-trivial fact here. But we are not using specifically that a contractible type is a set. Okay. Anyway, yeah. Let's continue. Cool. Going up here, I now want to do part B, which says that for any type A and for any truncation level K, is trunk KA, so that A is K truncated, is a proposition. That's what I want to show. So part B, so we want to show that, so really, okay, what I'm really showing here is that for all A in a fixed universe U, and so for all A and U and all K truncation, oh, that's, I don't like that. That looks like a pi. So for all truncation level K, we have that the type saying that A is K truncated is a prop. Okay, so this generalizes part A, which was at truncation level -2. All right, so we're gonna, K is basically this type that we've defined that basically is the natural number starting at -2, and it has the same induction principle starting at -2 instead of 0. So let's induct on K. So the base case, K -2 is exactly part A. Okay. So now the induction step. So assume that, assume we've proven that for all, let's say big X in U, and all, and sorry. So assume that, I didn't write this. This is not the way I want to write it, to be honest. I want to reverse these. So because I really want it for each K, I want a function from the universe to a type saying that is trunk K is a prop. So for all truncation levels, and all types in U, we have that this is a prop. Okay, so suppose we've proven for all types in U that is K truncated X is a prop. Okay, so we want to show that for all sorry to keep switching the variable names, but I think this helps eventually. So for all A and U is truncated K+1 at A is a prop. Okay. All right. So so what does it since we're using this induction on K, we're probably going to want to directly use the definition by induction on K for is trunk K, for is K truncated. So specific we want to show that for every let me say little x and y in A, we're okay. So yeah, we want to show that the identity type x equals y is K truncated. That's exactly the definition of K plus 1 truncated that we have. That all of its identity types are K truncated. Okay, so now so what do we? Okay, so how can we go about doing this? Oh, sorry. For every x, y is trait, I should finish this sentence. What we actually want to show is that this type is a proposition. Okay, cool. So now that we have that, let's see what we can use. We've assumed in our induction hypothesis that for any x in U, this type is truncated, is trunk K of x, is a proposition. So that seems pretty useful, right? Given that what we want to show is that this type is trunk K, x equals y is a prop. All that we need to notice is that x equals y is in the universe U because A is in U, and universes are closed under identity types. So we can directly apply induction hypothesis to conclude that, oh God, yeah, sorry, I'm so sorry, I messed up a little bit here because I made it seem like what we wanted to show was just that this is what we want to show actually is that we really want to show that an entire pi type we want to show that this entire pi type is a prop, because this entire pi type is exactly what this type is the same as. Okay, so yeah. So anyway, so I can directly apply the induction hypothesis to conclude that that each of these codomain types is a prop. But what I ultimately want to show is that the entire pi type here is a prop. So okay, any ideas on what we can do here? I want to get from the fact that that this type is a prop for each x and y in A, to the fact that this entire pi type is a prop. We've seen something earlier in the problem session that would help if we remember a while back now. Yeah, so exactly, problem 2, yes, exercise 2, problem 2 exactly gives us this result. Each codomain is a proposition. So when we so we have 2 pi types really here. This is shorthand for 2 pi types: pi x, pi over x, pi over y. The pi over y will be a proposition by exercise 2, and so since each of those pi types over y is a proposition, then we can use problem 2 again to then say that pi x, pi y is trunc x equals y is a proposition as well, which is exactly what we want. Okay, so that completes it by induction. That was supposed to be a check. All right, so the last thing I want to do, oh yeah, let me just first ask any questions on this proof before we go to the last problem I want to cover. Okay, so, okay, cool. Let's do the last one. Wait, did I? Yeah, sorry, this kind of split up a bit, but so let me, this is, so problem 4 has a long explanation to give a bunch of context to what we're doing, but the problem itself is really about taking a function f from A to B, so any function of that form, and considering a definition of f is an equivalence, and showing that that definition is itself a proposition. Okay, so that's what this problem is about, and the definition that we want to use is the definition that says that that the function f is contractible, which exactly means that each of its fibers is contractible. Okay, so each fiber over the fiber of f over y for each y in the codomain B is contractible. So using in the yeah, it is. Well, the cubical library, it is. I think so. You know, I know it's the definition used in the Cartesian cubical library, but the De Morgan library, which is I think the one you're talking about for cubical agda, I think so. Although I haven't used cubical agda in a long time, so check that on your own to make sure. Anyway, using the definition is equivalence. Yeah. Okay. So let me. There's some things to say about this definition. So using is equivalence f. Using this to mean, using this to stand for is contractible, using it to mean that f is contractible in this sense here. Let's show that, we want to show that this definition satisfies property 3, which is exactly that is a proposition. Okay, so now I do want to. So the solution is actually not that long. So so it won't take too long to describe it. I do. So before doing that, I want to briefly point out that in lecture a little while ago, Ulrich showed us that this definition of f being contractible is logically equivalent to the definition of equivalence as bi-invertibility. So bi-invertible. So so the type that says that F is bi-invertible, which is the definition of is equivalence that we used in the book, that it's the original definition that we use in the book of equivalence. We showed in lecture that these are logically equivalent types. So we have actually shown 1 and 2. Oh, sorry. This I need to say that we also showed that this is logically equivalent to F having a two-sided inverse. So if you recall those lectures when we did these logical equivalences, 1 and 2 are actually already proven for us. These are already facts that we've shown. So the question, the problem actually asks us maybe to, if we're feeling ambitious, to show, you might want to show that it also satisfies properties 1 and 2, but if you want, you can just appeal directly to the lectures from Ulrich in the past and be done. So all I'm gonna do is show that this definition of equivalence through contractibility satisfies property 3, which is that it's a proposition. Okay. So now that we've said that, let's do this. So there's a slick proof of doing this that makes it pretty short. So we want to show. So let's spell this out. We want to show that for every. We want to show that the pi type that says that for every y in the codomain B, the fiber F over Y that's not how we've been writing this. So I need to say is contractible. Okay. So this entire type, this entire pi type, we want to show is a prop. Okay. So now let's use exercise 2 again. Oh, fiber. What's the so the definition of fiber of F over Y is the same as the sigma type that says that gives an element of little a in the domain and a proof that F of X equals Y. So okay, if we want to show that this pi type, this entire pi type is a prop, let's do what we did in our previous solution in problem 3, where we use problem 2 to show that if we have that each of the codomain types here is a proposition, then we can conclude that the entire pi type is a proposition. So we've reduced it already to showing that. Let me so big C of Y. So it suffices to show that, to prove that C of Y is a prop for each Y in B. Okay, so how can we do this? So I want to prove that this type is contractible fiber of f over y is a prop. What can we do? Let's use, and this could be quick if we remember some facts that we've proven before this problem. In the problem session, not even in lecture, just in the problem session now. Not exercise 2 again, but so I'm really leaving you, I'm kind of leaving us one option by process of elimination of what we can use. And I'm talking about using the exercise to immediately deduce that this C of y is a proposition. Yes, exercise. So yeah, I see that you said exercise 1, 2, but exercise 3, part A, right? That immediately gives us that C of y is a proposition, right? Because we proved that. So yeah, so finally, problem 3, part A, implies that C of y is a prop, because it told us that for any type A, big A, is contractible A, is a proposition. So so it immediately tells us that C of y is a prop, in which case we're done. All right. So it's a pretty slick proof once we use what we've proven already. Any questions on that, on this proof here? So yeah, I think that covers it for this worksheet. Any final questions on what we've done on the worksheet here? So there's a question in chat. So is the type saying that a universe U is contractible a prop? So where U is a universe. And yeah, the answer is yes. So remember that U is just a type, and we yeah, I mean U is just a type, and we proved it. We proved that. So yes, as we've proven that this type is contractible of A is a prop for any type A. So we can specialize to the case where the type is a universe U. Okay, so I get the sense that those are all the questions we have. So I will stop the recording. Well, first let me stop sharing my screen. And I will stop the recording now.